Hello, I am R Balasubramanian from the Technical University of Munich, and in this presentation, I'll be talking about the complexity of coverability in bounded path broadcast networks. So let me begin by first describing what broadcast networks actually are. So a broadcast network is a model of distributed computation in which we have some number of agents. Okay, and these agents have no identities and they all execute the same finite state protocol. Okay, a finite state protocol, as the name suggests, consists of a finite set of states along with an initial state. So in the example given here, we have four states: a red bird state or the red state, a blue bird state or the blue state, a green state, and then a cool state because of the sunglasses. And we also have an initial state as illustrated by this arrow, which is the red bird state. Okay. And then there are transitions between states of this protocol, which enable an agent to either send a message or receive a message. So let us look at the example here. Let us look at the transitions of the example given here rather closely. Okay. So let us consider the transitions labeled by the message blue. Okay. So there is a transition at the red bird state. There's a self loop at the red bird state labeled by exclamation mark blue. This means that if an agent is at the red state, then it can send the message blue and still remain at the red state. Similarly, we also have a transition from the red state to the blue state labeled by the message labeled by question mark blue. This means that if an agent is at the red state and it receives a message blue, then it can move to the blue state. Okay. So for the sake of brevity, we assume that if we do not mention at any given state what happens when a message is received, then there's a self loop at that state upon receiving that message. For instance, we have not mentioned here what happens to an agent which is at the cool state when it receives a message blue. So we assume that when an agent is at the cool state and receives the message blue, it simply takes a self loop and stays at the same state. Okay. Now let us look at the transitions corresponding to the green message. So similar to the blue message, at the blue state, there is a transition, there's a self loop which allows an agent to send the message green. And similar to the previous case, from the red, if an agent is at the red state and it receives a message green, then it can move to the green state. Finally, if an agent is at the green state, then it can take a self loop and send a message cool. And if an agent is at the red state and receives a message cool, then it can move to the cool state by means of this transition. Okay. Okay. So far we have seen that a broadcast network is comprises of some number of agents, each executing the same finite set protocol and which can send or receive messages based on the transitions of the underlying protocol. What I have mentioned so far is the effect of sending a message or receiving a message. But what I have not mentioned is the following. So when an agent sends a message, I have not mentioned which are all the other agents that receive this message, right? I only mentioned what happens when an agent is at some state and receives a message, then the effects are given by the transitions of the protocol. So to mention who exactly receives a message, I have to specify some sort of communication topology between the agents in the network. Okay, so this is what I do now. So in a broadcast network, along with the protocol of the above form, we are also given some graph. We are given any graph on some number of nodes. Okay, so in the example here, we take the path graph on 4 nodes. Okay, the intuition is that each node has an agent which initially starts off at the initial state of the protocol. So here we have one agent in each of the 4 nodes of the graph, each starting at the initial state, which is the red bird state. Okay. Then at each point in time, an agent can send a message, which is then received by all of its neighbors in that graph. Okay. So in some sense, an agent broadcasts a message to all of its neighbors, and hence we get the name broadcast networks. So let me illustrate this by means of the example given here. So assume that we start at this initial path graph on 4 nodes, And the agent on the leftmost node broadcasts a message blue. This is then received by it only has one neighbor, the second node, which then receives this message blue and then takes this transition to go from the red state to the blue state. Okay. Now assume that in the second point, at the second point in time, the second node, the agent in the second node broadcasts a message green. This is then received by both of its neighbors, okay, who then move to the green state. Okay, and finally, assume that the third agent broadcasts a message cool. Okay, this is once again received by both of its neighbors, the one on the left and the one on the right. Okay, now the one on the left, by our convention, receives this message cool and simply stays at the blue state. The one on the right receives this message cool and then moves, and then according to the transitions dictated by the protocol, moves from the red bird state to the cool bird state. So this is the effect of this agent, of the third agent broadcasting cool and the other two receiving the cool message. Okay. In this way, starting from the initial graph, that is a graph where all the agents started off at the initial state, we have given an execution in which there is at least one agent which has reached the cool bird state. So we call this as an execution which covers the cool bird. That is, there's at least one agent which reaches the cool bird state. Okay. So now so with this definition of coverability being introduced, we can now consider the following problem, which is called the coverability problem. So here we are given a protocol P and a state F of this protocol, and we are asked to decide if the state F can be covered from some initial graph. That is there some graph of any size? Is there some initial graph of any size such that starting from this initial graph, there is an execution in which at least one agent reaches the state F. Okay. Note that it is not entirely clear that this problem is even decidable, because there is no a priori bound on the size of the graph that we have to start with in order to cover the state F. Indeed, as was shown by Delzano et al., this problem is in fact undecidable. Okay. So motivated by the undecidability result of this problem, the authors also considered another a restriction of the coverability problem, which is called the bounded path coverability. So in this problem, we are given a protocol P, a state F, and additionally, we are given a number K. Okay. Then we are asked to decide, is there some initial graph whose longest path is bounded by K, such that is there some initial graph where any path in that initial graph has length at most K, okay, such that starting from this initial graph, we can cover the state F. Okay. So in some sense, the longest path in the communication topology is bounded by K. Okay. Notice that since the underlying graph does not change along an execution, this means that if the initial graph, if the longest path in the initial graph is bounded by K, then the same is true for each graph in any execution starting from that initial graph. Okay. So the authors, in the same paper which proved the undecidability result for coverability, the authors also show that this restriction, the bounded path coverability problem, is decidable. Okay. And our main result that we get in our paper is that this bounded path coverability problem is complete for a class called F epsilon naught. Okay. So F epsilon naught is a complexity class in what is called the fast growing hierarchy. Now, to formally introduce this class, we need to define certain functions on ordinals and then relate those functions to like time hierarchies of Turing machines. And due to lack of time, I will not be defining this class formally, and we also do not need this. We also do not need a formal definition of this class for our presentation, because the hardness result comes by a reduction from an already known hard problem for this class. Nevertheless, in order to show how big this class is with respect to other classes in the fast-growing hierarchy, I will show some milestones of this fast-growing hierarchy, which are rather well known classes. which are already rather big and well-known classes, and show that f epsilon naught is much more huge than these already huge complexity classes. Okay. So one of the milestone in this fast-growing hierarchy is the tower complexity class, which is called F3, which is denoted by F3. And this class already contains non-elementary problems. That is, problems whose running time is not bounded by any fixed height of exponentials, which is already a huge complexity class. And then we have F omega, which already contains non-primitive recursive problems. It already contains what are called Ackermannian problems. And then we have f omega to the omega, which is called hack, and it already contains problems which are even more harder than some non-primitive recursive problems. Okay, and then epsilon naught it can be thought of as the ordinal which is obtained by the limit of omega to the omega, omega to the omega to the omega, and so on. And f epsilon naught is the corresponding class of this ordinal. So this is already much more huge than the hack complexity class, which is already bigger than the Ackermannian complexity class, which contains non-primitive recursive problems. So this shows that this bounded path coverability problem is a very hard problem in terms of computational complexity. Okay. So the upper bound behind this result is obtained by using a controlled bad sequences argument on a particular well-Quasi order for graphs. Okay. Due to lack of time, we will not be focusing at this, but we will rather be focusing at the lower bound, which, as I mentioned before, comes by a reduction from an already known f epsilon naught hard problem, which is the coverability problem for nested counter systems. We will now proceed to see what nested counter systems actually are. Okay, so for a given number k, we will define what are called k-dimensional nested counter systems, or simply KNCS. Okay, so a KNCS consists of two parts. In the first part, we have a tree whose depth is at most k, such that each node of this tree is labeled by an element from some finite set of labels. Okay, so in our example here, let us take k to be 2 and the set of our labels to be a, b, c, and d. So here we have a tree whose depth is 2, and each node is labeled by elements from the set a, b, c, and d. Okay. So in the second part of a KNCS, we have what are called k-depth rules. Okay. So each k-depth rule has a left-hand side and a right-hand side, such that both of these left-hand side and right-hand side are k plus 1 are tuples of length at most k plus 1 with elements from the set of labels. Okay. So let us look at this in a bit more detail. Now let us consider the rule R1. Its left-hand side is the tuple A, C, B, and its right-hand side is the tuple B, C, A. What this means is that if in our current tree, we have a path starting at the root labeled by A, C, and B, then we can apply this rule R1 and change the labels along that path to B, C, and A. Okay. So for instance, in our current tree, we have a path starting at the root labeled by A, C, and B. So we can apply this rule R1 and convert these and convert the labels along this path to B, C, and A. Okay. Now let us look at the rule R2, whose left-hand side is BB and whose right-hand side is CDB. That is, the left-hand side is of strictly smaller length than the right-hand side. Okay. So in this case, what this rule means is the following. If we have a path starting at the root labeled by BB, then we can apply this rule R2 to first change the labels of those two nodes to C and D, and then attach a new node whose label is B. So for instance, here we have a path BB. We first convert the labels of BB to C and D, and then attach a new node whose label is B. Now let us take a look at R3, whose left-hand side is CCA and whose right-hand side is B. Okay, so the left-hand side is of length strictly bigger than the right-hand side. So in this case, what we to apply this rule 3, we have to first find the path C labeled by CCA, and then we change the label of the root of the first node, that is the root, from C to D, and then completely remove the subtree rooted at the second node. Okay. So in our example here, we have a path of the form CCA. So what we do is we remove the subtree rooted at the second node, that is a subtree labeled by C, A, and B. We completely remove it and then change the label of the root to D. Okay. Okay, so this is what we obtained by means of this k-nested counter system. And the problem that we are interested in for nested counter systems is the coverability problem. So here we are given a k NCS for some k, and then we are given a label f. And we are asked to decide the following. So we are asked to decide if it is possible to start from the initial tree of the NCS, okay, the initial given tree of the NCS, and along some execution, if it is possible to start from this initial tree where the root can reach the label f. So starting at the initial tree, is there some execution where the root can reach the label f? Okay. And this problem was proven to be f epsilon not complete by Decker et al. And we will use this problem to prove hardness for our bounded path coverability. So the high level idea is that given an NCS n, we will construct a broadcast protocol P such that each tree of this NCS has a set of what we call representative graphs in P. Okay, and then we then make sure that each rule of this NCS is simulated by a suitable gadget of P among the representative graphs in P. Okay, so this is the high level idea, and we will now proceed to sketch the reduction behind this idea. Okay, so as mentioned, our reduction consists of two parts, and in the first part, what we have to describe is for each tree of the given NCS, we have to describe what a set of representative graphs are in the broadcast network that we consider. Okay, so let us take a running example of our KNCS that we have used before, and let us and I'll now try to describe for this tree the set of our representative graphs in the network that we construct. Okay, so to specify the set of representative graphs in our network, we have to first state what the state. We have to first mention the states of the protocol in our underlying broadcast network. Okay, so the protocol that we construct will have lots of states, among which the following will be a subset. So we take the set of labels of the NCS, which in our case is A, B, C, D, and we attach two new labels, which I'll call ST and FI. And then we take its cross product with the set 0, 1, 2, which is simply the depth of the NCS, which is simply the set from 0 to the depth of the given NCS. Okay. Having described this subset of the states, we can now describe what the set of representative graphs are of this given tree in our example. So we say that a graph of our broadcast network is a representative graph of this tree here if it satisfies two conditions. The first condition is that it should be a tree with labels from these states such that the second entry denotes the depth of the node in that tree. So for instance, here, this node has second entry 0, telling us that it's the root. These two nodes have a second entry 1, telling us that they are children of the root, and these two nodes have a second entry 2, telling us that they're children of depth 1 nodes, which is correct in this instance. Okay, and the second condition it should satisfy is the following. So after removing nodes labeled by ST and FI, the resulting subtree containing the root should give us back the original tree. Okay, so for instance, in our case, we remove these three nodes labeled with ST, FI, and FI, and then we get these, then we get the resulting subtree, this resulting subtree. Whereby, if we look at the first entries of the resulting subtree, we get back the original tree of the NCS. Okay, so you might wonder what's the purpose of having these ST and FI states if they're not even used in to sort of give the representative to sort of denote anything. But then you will see the usefulness of these two labels of these states in a short while. Okay. So this describes in some sense the set of representative graphs of the given tree in our broadcast network. And the second step is to construct gadgets in our broadcast network which simulate rules of the given KNCS. Okay. So let us do. I'll illustrate this. I'll give a very high-level idea of this by using our example. So we have this tree, and let's take this as a representative graph of this tree. So, and let's say we want to simulate the rule R1, which says if there's a path labeled with ACB, convert its labels to BCA. So we can interpret this rule in a rather natural and intuitive way in our representative graph. What we have to do is to simulate this rule 1, we have to construct to simulate this rule R1, we have to construct a gadget in our broadcast network which finds a path of the form A, 0, C, 1, B, 2 and converts it to B, 0, C, 1 and A, 2. Okay. And the very high level idea behind this gadget is that we can use broadcasts to simulate rendezvous communication. That is communication in which exactly one agent communication in which at each time step, exactly one agent broadcasts a message and one agent receives that message. So even though in a broadcast network, all neighbors of an agent receive a message, with respect, if you use this gadget, the net effect of doing so is as if just one neighbor received the message and all the others just did not receive the message. Okay, this is a very high level idea behind this gadget. Okay, and using this gadget and the effect of one of the effect of using this gadget will be exactly what we mentioned at arriving at this representative graph of the tree that we will get by firing R1. Now let's say to simulate R2, which says find a path of the form BB and convert it to CD and then add a label, add a new node with B. To simulate this, first notice that in broadcast networks we can neither create nor destroy agents, right? So this is kind of hard to simulate, whereas in NCS we are allowed to create and destroy nodes. So how do we do this? So to mitigate this problem, what we do is that we construct a gadget which finds a path of the form B, 0, B, 1, ST, 2 and converts it to C, 0, D, 1 and B, 2. Okay. So in some sense, we are using the ST states to act to serve the purpose of creating new nodes. Okay. And similarly, so this is the net effect of using this gadget and the net effect of firing this rule on this tree. And similarly, to simulate destroying nodes in our tree, so for instance, to simulate the rule R3, what we do is we construct a gadget which finds a path of the form C, 0, C, 1, A, 2, and converts it to D, 0, Fi, 1, and Fi, 2. So in some sense, we are using the Fi states to simulate destroying nodes in the original tree. Okay. And this is the net effect of firing R1, R2, R3 from what we started. And this is the net effect of firing the corresponding gadgets from the starting representative graph. Okay. So this gives us a high-level overview of these gadgets. And to wrap up, so notice that with respect, I mean, what you have shown with these gadgets is that for every tree T of the NCS and every number N, there is a representative graph of T in our broadcast network, which can simulate N steps from T. Okay. Hence, the initial tree I in the original NCS can cover a state F if and only if some representative of I can cover F, 0 in our broadcast network. Okay. But notice that in the bounded path coverability problem, we are allowed to start at any initial graph, and we need not necessarily start at initial representative graphs. So how do we get around this? Well, we get around this by constructing another sort of seeker protocol that starts at any initial graph and arrives at a representative of the initial tree. Okay. And then putting the seeker protocol along with the simulator protocol that we get by composing all the gadgets, the reduction then becomes complete. Okay. So to conclude, we have looked at the coverability problem in broadcast networks, and we have shown that over bounded path graphs, this problem is F epsilon not complete. And the lower bound for this result, and the lower bound result here was obtained by giving a reduction from nested counter systems. Thank you for your attention.